So in this video, we're going to use the limit definition that we saw in the previous video to find the exact area under a curve. So it says find the area of the region bounded by the graph of f of x equals 4 minus x squared and the x-axis on the closed interval from 1 to 2. So the first thing to recognize is that 4 minus x squared is a downward opening parabola. So if I were to draw it, it would look something like this. So I'd have a vertex up on the y-axis. That's not very parabola-y. And we'd have an intersection with the x-axis at x equal to 2, because when I plug in 2, I get 2 squared is 4, and 4 minus 4 is 0. I don't really need to know the y-axis, so in order to draw things well, in order to use the formula for the area of a region, I probably want to give myself a little bit of drawing space. I'm going to put the 1 over here for my closed interval from 1 to 2. So remember, the area is going to equal the limit as the number of rectangles we use to estimate area goes to infinity. We want the sum from I equal 1 rectangle to the nth rectangle of f of c sub I, where c sub I is just any x value on the ith interval. And we multiply by delta x, which is the width of each rectangle. So the first thing we want to deal with is finding or determining delta x, the width that each rectangle will need to be. And we're going to use n rectangles for our area estimate. So remember, delta x is just b minus a over n, where b and a are just the two numbers establishing the closed interval over which we're working. We just need the length of the line segment on the x-axis over which we're working to get the width of each rectangle. So in this case, it's going to be 2 minus 1 from our closed interval right here over n, where n is the number of rectangles we use. So this just simplifies to 1 over n is the width of each rectangle. So remember, we're going to start at a left bound of 1, and we're going to construct rectangles. We're going to construct n rectangles, and we can use left endpoints. We can choose to use right endpoints. We could choose to construct them using the midpoints. We can construct them however we want. So for convenience sake, I think that right endpoints are going to be kind of the simplest way to do it. So over from 1, which is the first coordinate on the interval, I'm going to get my next tick mark showing up at 1 plus 1 times delta x. That's where the next number will be, because the width of the rectangles needs to be the delta x. So I always add delta x to get to the next tick mark. But our delta x is just the 1 over n. So I'm going to get 1 plus 1 times 1 over n as my tick mark here. That will be the x coordinate right here. And from there, you know that you just draw up. If we're doing right endpoints until the top right corner of the rectangles on the graph, we move over and down to the first number on our closed interval. And then to get the next place, you would just pop in the next number, which would be 1 plus, and now it's going to be 2 delta x's. So it's going to be 1 plus 2 times delta x, or just 1 plus 2 times 1 over n. And you would construct your next rectangle, and then dot, dot, dot. We would continue this process, and at some point we would get to the ith rectangle, and we'll have tick marks here and here, and we know that this is x sub I, and we know that this right here is x sub I minus 1 if this is the ith rectangle. Sorry, if the next rectangle is the ith rectangle. So we would construct that by drawing up, over, and down. This would be rectangle number I, and there are n of them, so we don't know how many it's going to be, but we're going to end when we get to the end of the interval. And what we want to recognize is that 2 is just going to equal 1, the first number on the interval, plus, and it's going to be n times delta x, or in other words, 1 plus n times 1 over n. N times 1 over n is equal to 1. 1 plus 1 is 2. So this will be the last right endpoint for our rectangles. X sub I would actually be 1 plus I times 1 over n. So to get the area, what we want to recognize is we're going to take the limit as the number of rectangles goes to infinity. We're going to do infinitely many rectangles. And then we're going to take the sum. We're going to go ahead and use the right endpoints because that's probably the most convenient thing to do, because the counting starts at 1. It's going 1 plus 1 times 1 over n. 1 plus 2 times 1 over n, all the way to 1 plus n times 1 over n. So we could use right endpoints by taking the sum from I equals the first right endpoint to the nth right endpoint. And then we need to have a representation for those right endpoints that we can plug into our function. So we need to represent the number for the ith interval that's getting plugged in. And so we want to recognize that it's really going to be 1 plus I times 1 over n represents the ith right endpoint. So I'm going to plug in here 1 plus I times 1 over n, where 1 over n is just that width, or that change in x. And then times, we need to multiply by right here delta x. But delta x is just the width of each rectangle, and the rectangle widths are 1 over n. We've calculated that right here. So it's going to be times delta x, but delta x is 1 over n. So this is the area under the curve. And what remains to be done is that we actually do this calculation. So once we have extracted the sigma notation to calculate the area of the formula, we don't need the picture anymore, and we don't need to remember this formula anymore. This is just a matter of calculating sigma summation notation. So I'm going to go to the next slide so I have extra space to work on it. So now you just start stepping through this and simplifying. The sum, the area is equal to the limit as n goes to infinity of the sum from I equal 1 to n of f of 1 plus I over n. There might be some convenience in recognizing that 1 plus I over n, if you find a common denominator, you would multiply by n over n. So this would give you n plus I over n. This might be a useful way to write it. So I'm going to step down a line. I'm going to say this is the limit. As n goes to infinity, I'm taking the sum from I equal 1 to n, f of the input. So I'm going to take the 1 plus I over n, which also equals n plus I over n. I'm going to plug it into my function. So I'm going to plug it in. Actually, I'm going to give myself a little space here. I've got a 1 over n right here, which is a constant. I want to factor that out of the summation. So I'm going to get 1 over n times the sum from I equal 1 to n of, plug the 1 plus I over n into the function f of x. So I'm going to get 4 minus, and instead of plugging in it as 1 over I over n, I'm going to go ahead and plug it in as n plus I over n in the common denominator form. So I'm going to go n. You don't need to do that. I'm just making a personal decision to do it that way. So there's the replacement of the function input into the function, and now we need to simplify things. So this is going to equal the limit as n goes to infinity of 1 over n, the constant we factored out, times the sum from I equal 1 to n of 4 minus, let's square out the numerator, n plus I squared is going to be n squared, plus, we'll get n times I twice, so 2ni, plus I times I is plus I squared, and this will all be over the n squared. And then if I wanted the common denominator, I would just multiply this 4 times n squared over n squared, which is still equal to 4. So if I do that, I'll get equals the limit as n, that looks like an h, as n goes to infinity of, I have an n squared showing up in each denominator, so we can factor the n squared out because it's a constant. So I'll get 1 over n times n squared is n cubed, times the sum from I equal 1 to n, and I factored the denominator out, so I'll just get numerator terms. This minus needs to distribute into each of the terms. So I'm going to get 4n squared minus n squared is 3n squared, minus plus is going to be minus 2ni minus plus is minus I squared. And then we can use summation tools or rules to break apart the summation, so we get the limit as n goes to infinity of the 1 over n cubed times, we'll break this into the individual sums. So I have a constant here, 3n squared. So I'm going to have the sum from I equal 1 to n of the constant 3n squared minus twice n, so factor the twice n off of the summation, so we get the sum from I equal 1 to n of just I, so 2n times I, factoring that constant out, minus the sum from I equal 1 to n, that's a horrible I, of just the I squared term. And this is an infinity right here, even though it looked horrible. And once I get it to this position, I can now use the summation formulas that we developed in previous videos to simplify our calculations. So I'm going to get equals the limit as n goes to infinity of 1 over n cubed times, this is the sum from I equal 1 to n of a constant. So if we have the sum from I equal 1 to n of a constant, we multiply the constant times n. So in this case, it's going to be 3n squared times n is just 3n cubed minus 2n times the sum of the i's. But the sum of I from I equal 1 to n is right here. The sum from I equal 1 to n of I is just n times n plus 1 over 2. So I'm going to multiply by the sum of the i's is n times n plus 1 over 2 minus, this is the sum from I equal 1 to n of I squared, but the sum from I equal 1 to n of I squared is just given by this right here, n times n plus 1 times twice n plus 1 all over 6. And then if I wanted to, I could do a little bit of common denominator finding. So I could take this guy right here. This was a minus sitting here. So I could multiply this by 3 over 3. And I could multiply this by 6 over 6 to get a common denominator of 6. So one last little simplification before we actually calculate the limit. So we take the limit as n goes to infinity of, I'm really going to have a denominator of 6 times the n cubed can distribute in. And in the numerator, I'm going to have 6 times 3 is 18n cubed minus 3 times 2 is 6. N times n is n squared times n plus 1 minus, and we'll just leave this numerator like it is. And you're going to see why I don't want to multiply this all out in just a second. So we could multiply this all out and combine like terms, but we don't need to. What I want to recognize is that I have a polynomial numerator. This is a polynomial, and it's actually of degree 3. I have an n cubed here. I have an n squared times n is n cubed here. I have an n times 2n is a 2n cubed there. So the highest degree term in the numerator is an n cubed. So I have a polynomial in variable n in the numerator, and I have a polynomial with variable n, a degree 3 polynomial, 6n cubed in the denominator. That means this is a rational function. And when we're taking the limit as n goes to infinity of a rational function, we only need to take the limit of the highest degree terms. And this is a result we've already established it. This was established in pre-calculus, and this was established again at the start of this semester in Calc 1 when we were looking at how to take limits of different types of functions as n went to plus or minus infinity. So the key here is I'm going to take and find the area. So I'm going to bring my calculation up to the top of the other page so that I have some room. I'm going to find the area, which is equal to the limit as n goes to infinity of, because I have a rational function, I only am worried about the highest degree term in the denominator, which is the 6n cubed, and the highest degree term in the numerator. But the highest degree term in the numerator is going to come by combining the third degree terms from the numerator. So this limit is the same as taking the limit of 18n cubed minus the n cubed term here is going to be 6 times n squared times n is 6n cubed, and then minus, and then I need the third degree term from this guy, so it's going to be n times twice n is 2n cubed. So this limit is just the limit of the ratio of the highest degree terms because I have a rational function. I don't need to expand and multiply everything out to calculate this limit. So now this equals the limit as n goes to infinity of 18 minus 6 minus 2 is just 10n cubed over 6n cubed. And n cubed divided by n cubed equals 1 as long as n is not equal to 0. But n is going to infinity, so we know that n is not going to equal 0. So this simplifies to 10 over 6. I can drop the limit notation because I just took the limit and now I have a real number sitting here. The limit's been taken. And then I can simplify this to 5/3, which is the exact area under the curve 4 minus x squared on the closed interval from 1 to 2.